a work that we do with some colleagues from Barcelona. We build up a database. If you have an Android phone, you can install an application that measures the power that comes to the Android phone and send it to our database, so that you can go to the database and see in Vigo how much energy you can collect from the air. So why we are doing this is because if you want to know if you can have a sensor that is powered by radio, how much radio you have in each piece of the rod. Okay, so if you want this is going to stay here. So and okay, I will pass now. Okay, I will pass now to the second talk, and the second talk is more technical. So I'm not going to talk about what's the future of things and what we'll want. We'll go more technically and more deep. So I will talk about test signals for characterization of nonlinear microwave devices. This is what we are going to talk now. So I will talk briefly about a brief introduction, typical test signals, how I measure a phase measurement in the two-tone intermodulation, what is a special design two tones for nonlinear derivation, multisigns, and dynamic impacts also of these multisigns. And in order to say why I'm doing all this, and this brings me back to what I talked briefly ago, which is I have my system, but I love to have good models for this, so that I can use MATLAB or I can use any type of simulation tool to extract what is happening in my system. But in order to extract these, let's say, good models, I have to find a way to measure and to extract those models in the laboratory. And the problem, as you saw, when I say that a power meter works differently with one tone, a sinusoid, or with two sinusoids, it happens the same here. So what is a problem for my stimula, let's say in the laboratory, is that it should excite the largest possible range of, so it should excite the maximum as I can from my device, because if I don't measure it, I cannot model it, and this is a problem actually on this. It should allow simple measurement procedures. I don't want to spend 1 week in the lab. I know people do, but I don't want to spend 1 week for extracting one simple model. I want, for in the industry, we should be very fast as I can. And of course, it should reproduce the responses of my device as much as I can. If not, I said, you design something on the computer, you build it, and it's another thing. It's not what you design. So it should actually represent this. And this brings me to the problem of nonlinear system. What is a nonlinear system? Well, a nonlinear system actually can be defined as a system that does not obey superposition and does not obey proportionality, if you want. Okay? What that means, it means the following. Imagine that I have a nonlinear system, and this is the frequency. So I put at input one tone. What is one tone? Is a sine wave, right? So this, I'm only showing the positive part of the spectra. So this is a sine wave at omega 1. This is the direct, if you know Fourier transform, this is Fourier transform of the sine wave, okay? What happens if I pass this through a nonlinear system? You can represent a nonlinear system. The best way is by a polynomial. So what happens at the output? The output, you'll have a replica of the input, but you also have a second harmonic, a third harmonic, and so on, okay? So you can have harmonics of these signals. Now imagine that I have another signal. What I have at the output? Signal, second harmonic, third harmonic, and so on. Now, I combine these two signals. So I have what it's called a two-tone signal. Two sine waves. Okay? I put two sine waves at the input. And my question is, what is the output? Is the combination of the two? Well, if it was a linear system, it will be the combination of two. But I said, nonlinear system does not obey superposition, so the output of a two-tone signal is much more complex than the combination of two. Okay? So you have the replicas of the input, you have the harmonics, 2 omega 1 and 2 omega 2, you have the 3 omega 1 and 3 omega 2, but then you have all mixing of this. You have this combined with that gives omega 1 plus omega 2. This combined with that minus that one, it gives this one, and so on and so on and so on. Okay? And here I'm only representing the output as if I have a 3-order polynomial, so x cubed. If I have x4, x5, this is becoming crowded, of course. Okay? And the other problem we have is that this is a typical GSM signal, this is a typical 3G signal, and these are the time domains of those signals. And then I start to have a problem, that is spectra enough to represent the time domain? Probably not. Can I use the spectra to represent time domain? I don't know. What is the best signal to use? I don't know. Okay? Since nonlinear systems does not obey superposition, I can tell you one thing. If I want to use my system with a 3G, then I have to measure it with a 3G at input. The problem to measure it with a 3G at input is that it's very, very hard to measure those signals. So can we design or can we measure my signals with a simpler, or measure my device with a simpler signal? That's what we are going to see today. But only to show you another strange phenomenon of nonlinear systems. What I'm representing here, this is a transistor that we have there in the lab, and this is additive white Gaussian noise. So we go to the lab, we create a noise signal, and we filter that noise signal. So actually what you are seeing is the spectra of that signal. You see? Spectra, this is the filter, and we are putting noise at input. So we pass this signal through our nonlinear system. What is the output? You have a gain, it's like an amplifier, and then it creates this, it's called spectral regrowth. I will talk about this later on, but this is nonlinear distortion, okay? Then I go to the lab and I create another signal. Another signal, which is a wideband CDMA, so something like 3G if you want, exactly with the same spectra. You see? It's the black curve, exactly with the same spectra. And I pass it through my nonlinear device. And I go to the output. And what is the output is completely different. Okay? You see the output, the gain is the same, the linear part is the same, the nonlinear part is completely different. And this creates a bell. That is, so how can I measure this? Because if you go to the lab and if you extract your model with this, what is going to happen? It gives you bad results, which means that you build a device with this model, you give to your customer, and you have higher distortion here, and the customer sends the model, the instrument back, saying, no, this is not working. It is not filling the mask. So my question is, we have similar power spectral density, we have similar integrated power. If you integrate the power, you have the same power, the power spectral density is same, but you have completely different spectral growth. That is, you have completely different behavior of your system. And this is actually my question, that is, what type of information can I gather for each stimulus signal? And these include one single sinusoid, two single sinusoids, Gaussian noise, multi-sign signals. I will talk about that, or other type of signals. What can I use in the lab? So let's go step by step to see what each signal gives you in a nonlinear behavior in the lab. So the first one I have is one tone. I put here one tone, and I should have it here, but I don't have it, but I have a pen. So if you... Okay, very, very fast. If you have cosine of omega t, like I have there, and a nonlinear device, I told you that it can be represented by a power series. Okay, and of course, I'm only stopping here. If I substitute my signal now, this is the output. If I substitute this with x, you'll have y is equal to 1. Oh, sorry about this. X cosine of omega t plus a2 cosine of omega t squared plus a3 cosine of omega t cube. Okay? So if I decompose this now, this can be like this, but if I decompose this is a 2 over 2, and this is 1 minus sine of 2 omega t, something like this, okay? And if I decompose this will give me a frequency at omega and another frequency at 3 omega, if you decompose this. So actually, this is where the second harmonic comes from, this is where the third harmonic comes from, and I also have a DC component coming here, which is the RF to DC converter that we talk about later on. So if I look here, if I put this signal at input, you will see a DC. I'm not considered DC now. I will see 1 omega 1, which is there. I have 2 omega, which is there. I have 3 omega, which is there. And if I consider more terms, I will have more harmonics. Okay? So what can I do with one tone? First thing I do with one tone, I can pick up the one tone and start changing the frequency. If I change the frequency and if I measure the output, I can represent the behavior in terms of amplitude of the output versus the input. Okay? And this is normally what I call the gain, if you want, or the transfer function, if you want. And I can measure this in amplitude, and I can also measure the phase. And since this, if I use a linear system, I can use superposition. So this actually represents everything I need. This is the S parameter, the S21 if you want. Okay? The problem is when I start to change the amplitude of my input signal, so I don't consider a single amplitude, I try to change the amplitude. What I will see that if I measure the output amplitude divided by the input amplitude, what you'll see is that this is the input power, this is the power gain. You see that the gain is more or less constant, and then will start to decrease. Why? Because you are all electrical engineers, right? So you know that if you have a, let me try like this. If you have a transistor here, imagine that you have some kind of amplifier or something like that. What is going to happen? You have a small signal and the output is going to be an amplified version of that small signal. You increase this small input signal, what's going to happen at the output? Start to collapse, right? So you can increase this as much as you can, but this will not increase more. It will collapse. It will create, actually in the limit, if you don't burn the transistor, you create a square wave. Okay? So actually, what you'll see is that the gain starts to decrease because you are increasing the input, but the output doesn't increase, so the gain decreases because the relation decreases. So this is called, from a nonlinear point of view, this is called AM to AM conversion. You are converting amplitude at input to amplitude at the output. Okay? And if I measure the phase relationship between the output and output, I will see this. For what it's called small signal, so when the device is behaving linearly, you'll see that the phase is constant. But when you start to put the device working in a nonlinear fashion, the phase is going to start to change. So the phase of the output is going to start to change compared to the phase of the input. And this is called AM/PM, which means that I change the amplitude modulation and I'm changing at the output the phase modulation. AM/PM conversion. Okay, so I can gather these values here, and how can I measure this? With a network analyzer. Okay, network analysis is very easy to do. I have a generator, I have my device under test here, I put an input signal, output signal, and if I measure the frequency, I measure the linear behavior, let's say. If I measure the amplitude, I measure those values that I show you. The other thing I can measure with one tone is a figure of merit called total harmonic distortion. What is total harmonic distortion? As the name says, is the summation of the harmonics. Okay, you can measure the power of the harmonics, you do some calculation, and you have the total harmonic distortion of your device. So it gives you a feeling if your device is very nonlinear behaving or if it's more linear behaving in that sense. And I can measure this with a spectral analyzer. So this is what I can do with one tone, nothing more. What are the problems? First, one tone gives you this and this, but nothing inside. Which means that imagine that you have a power amplifier that has a very tiny filter at the output. what happens, the filter is going to kill the harmonics, and you don't see nothing, and you say, okay, my system is linear, because you are not seeing these harmonics, okay? As much you can see the compression of the fundamental, nothing more. You can see the compression of this. The other thing is that despite you can have some DC, you don't see nothing here. Nothing appears of what we call baseband signals, or some people also call it video bandwidth. So nothing appears on the video bandwidth because it's one tone. It's actually an unmodulated carrier, so no information is there, okay? So let us now move to a two-tone signal. If I pick up a two-tone signal, so this is a cosine at omega 1, another cosine of omega 2. You can put it on your Taylor series, you can expand all that, and you'll see that the output is going to happen at all combinations of omega 1 and omega 2, where m and n that I'm representing here are integers. Which means that if I go to the third order, m plus n should be below or equal to 3. Okay? And if I do that, I will have all these components appearing at the output. So two tones, intermodulation, and so on and so on. I don't know if I have it here. Yes. Okay, so here again, there's also a very important thing, that is, if I filter out these components and I filter out that components, which is normally what I do in narrowband systems, I continue to have these tones appearing here, you see? These tones are called intermodulation, okay? In this case, because they are something like 2 omega 1 minus omega 2. What that means, it means that I have omega 1 and omega 2. I start to combine them all the possibilities, and there is one that is 2 omega 1 minus omega 2. You see that m is 2, n is 1, so m plus n is equal to 3. So this is a third order process. And you have 2 omega 1 minus omega 1, 2 omega 2 minus omega 1. What is the problem here? If these tones are very close to each other, imagine GSM. You have 900 megahertz. GSM band is 200 kilohertz. They are very close to each other, which means that this tone here is going to appear 200 kilohertz near, and the other 200 kilohertz near that. What is the problem? You can filter, okay, but it's almost impossible to kill them. They will also appear there. You can use SAW filter, okay, but then you have problems with what you're going to lose and so on. So actually, it's more difficult to get rid of these tones here, okay? And what I can do? Well, I can go to my signal and I can increase A1 and A2, and if I increase them with the same power, I can make these plots. So this is the variation of omega 1 and omega 2, in this case is omega 2, okay, for input power. So this is output power, input power. What I will see that they will, as I increase the power at input, like I said in the transistor, when I'm increasing, if it's behaving linearly, I'm increasing and the output is increasing also, okay? So you will increase up to a point where it starts to compress because the output doesn't increase more. And if I look to these components here, what I'm going to see is that these components come from x cube. So if I have 1 dB at input, this is cube. So I will have 3 dBs increase at the output in terms of the harmonics, you see? So what I will see that my intermodulation is going to increase at 3 dBs for each 1 dB that I increase at input. So what you'll have is a curve like this, you see? And when it starts to compress, then here I can have different behaviors. I can have this, I can have something like this, I can have strange behaviors, okay? What is important here for a microwave or for a radio engineer? The important is two figures of merit. I don't know if I have the other one here. No. One is when my real curve starts to deviate from my ideal curve by 1 dB, I have one figure of merit called 1 dB compression point. What that means, it means that my gain is compressed by 1 dB. And why is this important? Because this is considered the edge of the nonlinear distortion behavior. So at this point, it will start to compress very fast. Okay, this is one problem. The other, or one figure of merit, sorry. The other is the following. Imagine that this is increasing 3 dB per dB, and I extrapolate this. And I extrapolate this curve also. They will join in one specific point. Okay? This point is called intercept point of third order, IP3. This is very important for power amplifiers, for instance. All data sheets come with this. It's very important to consider here one thing. This doesn't exist. What that means, the amplifier never goes there. Okay? If you try to operate your device at the IP3 input power, it will burn. Why? Because this is an extrapolation. Okay? Which means that you can say, okay, so why I need something that doesn't exist? It's very important because since I know this point, if I know this output power, these are two lines, so I can know exactly what is the relationship between my fundamental and the third order distortion, you see? So I only need to know one point and another point, and I can extrapolate this one. So this is why IP3 is very, very important. But it doesn't exist in the sense that I cannot go there and measure it. I can only extrapolate from a curve like this. And you can have third order intercept point. You can also have second order intercept point. This is the signal going up at second order. Okay, second harmonic if you want. In this case, it's not second harmonic, it's another second order that appears at the video bandwidth or baseband. And why is this curve important? For mixers. Very important for mixers, because you can know where they start to compress somehow in that sense. Okay? And of course, with this, you can define what it's called the intermodulation ratio, which is equal to the fundamental power divided by the intermodulation, and this can be all extrapolated from those curves, measured curves. And how can I measure this? Two generators in the lab. Normally, I put here filters and isolators, power combiner, my device, and a spectrolyzer. This is traditional way to do. And just a parenthesis, why I do this? I can go and not use this. Generator, power combiner, that's it. What is the problem? The problem is that this was designed for a 50 ohm system. This sometimes is not a 50 ohm system, it's approach to 50 ohm system. So you'll have some kind of return loss here. So you have some kind of return wave. What will happen? This signal will not be perfectly matched here. So this signal goes here, enters this generator, creates a nonlinear distortion, comes out, and you measure that huge nonlinear distortion. You say, my device is working bad. And your device is not working bad. The problem is that you are generating distortion here, and actually you are measuring error. Okay? Garbage. So what we do with this, first this is used to kill the harmonics of these generators. Because this is another important problem. When you go to microwave office, when you go to ADS, you pick up a generator and you have a perfect generator. It doesn't have phase noise, it doesn't have harmonics, it doesn't have, everything is good. It has a 50 ohm load, everything is good. You go to the lab and you have harmonics, you have phase noise, you have all this. And what is the problem is that it can mask your device. So you think you are measuring your device, and no, you are measuring the instrumentation on the lab. So this is important to know that these filters kill the harmonics. And these are isolators, which means that in this sense, they will attenuate 0.5, 1 dB. But if the signal comes back, it will attenuate 20 or 30 dBs, which means that even if I have a signal coming here, it will be attenuated 20 or 30 dB, so it will generate lower values of distortion there. So this is very important to use when you want to guarantee that you are doing a very good result or a very good measurement. So this is output, and what we see is that, okay, I already have inside information, I didn't have that with one tone, and now I have this video bandwidth here, you see. The problem what I say here is that, as I said, when I want to extract a model, I want to excite the most or the biggest number of state spaces of my system, because I want to capture all the information. And when I'm doing this, I'm only exciting one frequency of the video bandwidth, okay? And this is important to see. In one tone, if they are separated by 200 kilohertz, as I said, this signal will appear at 200 kilohertz. And this is important because it can change completely the behavior of your device. Actually, I'm not talking deeply about that, but one phenomena for power amplifiers is called memory effects. This is the memory, let's say, if you can have in your device. This is exciting the memory effects of your device. And what is the problem? The problem is that you use two-tone and you only have one frequency here. Or if you go to higher orders, you'll have harmonics of these ones. But what means that you are not measuring, you are not exciting the frequencies here, you see? You are only exciting this one. So one thing they do when they want to do memory effects, they pick up the two tones and they do this. They change the separation between the tones. And then when you do this, if you look to the spectrum, what you is going to see, this will go up and down. But again, they are expecting that superposition will work at video bandwidth. Okay, because you are not exciting everything at the same time. You are exciting one and another and so on. And this can be done, I will come here. This can be done actually in an automatic way in the lab using a function like this. You have a cosine, another cosine, and you change this delta. So actually, what you do, you create a figure or you create a signal that they call it sharp signals. Okay, what is a sharp signal? This is the frequency, this is the time. So actually, the tones will go up and down like this, okay, with time. So actually what you see in the, if you use a spectral analyzer, you see the tones going up and down, okay? And this is important, why? Because I can do a spectrogram with the real-time signal analyzer that I show you, and you can see what is happening to the intermodulation over time, okay? Okay, I'll go back. Okay, I can follow this. And actually, if you capture figures, you can see tone spacing 1 kilohertz, 2 kilohertz, 4 kilohertz, 8 kilohertz, 16 kilohertz, 32, 40, and you can see what is happening on each for each tone space inspiration. And this is very important, as I said, to excite long-term memory effects, or what we call video bandwidth in that sense. But real signals are not two-tone signals. Okay? Real signals are much more complex. And I said, nonlinear systems, they're not obey superposition, so two-tone signals are good, but they don't cover everything. So another important signal is what it's called a multi-sign signal. What is a multi-sign signal? As the name says, multiple signs. More than 2, 3, 4, 5, 100, 1000 tones. If I put here 1000 tones, what is going to happen? Again, if you put in the polynomial, you'll see the output is going to be like this. So where omega 1, omega k, omega... So you have all the combinations, possible combinations you can have in all those tones. So you'll have a baseband that is like this. This is distortion appearing in bands, second harmonic, third harmonic, and so on and so on. Here, you see, I'm exciting a lot of other tones at video bandwidth. I'm no longer exciting only one frequency at video bandwidth. And what I can measure with this? Well, the most important measurements is, this is the input spectra, the output is going to be like this. And remember, all these new tones are mixing tones of the other ones, okay? And this is called spectral regrowth. It's like the spectra is growing there. Okay, you don't have, but it regrows there. And actually, what you can measure, if you relate the input power with the output power, you can measure the gain. And if you relate this power with the power appearing here, you measure one figure of merit called adjacent channel power ratio, which is one very, very big important problem at the moment. Oh, sorry. And actually, this should not happen. Okay. Actually, if you measure the distortion, because now you have combinations of all tones, so some will fall here, but you have also tones appearing inside. They will fall on top of your signal also. And this can be measured with something that is called noise power ratio. So I can measure the distortion that is appearing inside. Okay? And how can I measure this? I can measure this using a generator, a multi-sign generator, device under test, and spectral analyzer. Okay? The problem with the multi-sign, and this is what I showed you before, I can go to the lab, I put this signal and I said, okay, I'm exciting a lot of signals, I'm exciting a lot of information, so I extract a good model that represents this, and then I build my system and the results are different. And I said, okay, what happened here? What happened with the multi-sign is the following. A multi-sign, as I said, is a summation of signs, okay? And if what I'm showing you here is, I consider 10 tones, 10 signs, and I consider that amplitude of the signs are equal, exactly the same. What that means? Same power, same spectra. But then I change the phase of the signs. So in this case, all the signs are synchronous, same phase. And what happens to the time domain if I go there with an oscilloscope? This is a MATLAB code, you can do it, it's very easy. You see that you have peaks sometimes and almost nothing other times. Then I go with my formula and I choose the phases not 0 degrees but random. I put the phase as random phase, in each tone as a random phase. And this is the output. Okay? This has exactly the same y-axis. What that means? It means that if I use this sign, my transistor, imagine that my transistor at 4 volts starts to compress. What it will happen here? Huge distortion. What will happen here? Nothing, no distortion at all. You see? So that's why when I show you, in the beginning I show you white Gaussian noise and I show you WCDMA, they seem similar, but the results were completely different. And this happens why? Because I forget something. I forget to look. When I look to the spectra, I normally, or mainly, let me explain this like this. When I look to the spectral analyzer, I'm looking only to the absolute value of the power. I'm not looking to the phase relationship. I'm only extracting the power of my device. Okay? What happens is that I should start to look how statistically the signal behaves over time. So this gives me information of how the signal will behave. It's going to take 10 volts, 5 volts, 4 volts, how it will change over time. So we start, and most of the vendors start to use a plot for signals called complementary cumulative distribution function. So you know what is the probability density function. Probably you have heard about cumulative distribution function. This is the complementary of that. So it's 1 minus the cumulative distribution function. What this gives me, and forget I don't have the axis here, but this is the probability, this is the amplitude of my signal. What is giving me this information is telling me that this signal has peaks that are lower than this signal. Despite these two signals have exactly the same spectra. You measure with spectral analyzer, they are exactly the same. But the behavior, statistical behavior over time is different if you consider this one or if you consider that one. That's why most of the new instruments allow you to click on a button to see the cumulative distribution function of your signals. Okay? And I go and I try to show you different signals. So here I have the cumulative distribution function, or sorry, this is the probability density function of a two-tone signal, of a uniform distributed multisign. What that means? It means that I choose phases that have a uniform distribution, and this is a Gaussian distribution of the phases. And these are three different, let's say, statistical behavior of my signals. I measure the two-tone distribution I measure intermodulation ratio of 31 dBs, and then I pick up the uniform distribution and the Gaussian distribution. Let me just say, let me go back. All these three signals have exactly the same power. So if you go there with a power meter, you measure exactly the same average power. And what you see is that two-tone gives you 31 dB of distortion, and the others, actually the Gaussian approximates quite well the intermodulation of two tones, and the uniform gives you 38 dBs. And you see the spectra is completely different. And this is not due to the power I'm having or sending inside my device. Let me also say here that power amplifiers for base stations were used mainly for one-tone GSM. So people were using one carrier GSM, they use a power amplifier. Power amplifier says maximum input power 2 watts, and they were using that at 1 watt. Imagine this, okay? So with the increase of channels and mobile communication and so on, they said, okay, now I want to send 3 GSM signals to the air. If I want to send 3 GSM signals to the air, if each one has 1 watt, I looked to my power amplifier and I said, okay, I was operating it at 1 watt, so let's do what it's called input back off. So I will operate my device 2 watts below. Okay, so instead of being operating my device at maximum, I will reduce 3 watts. What we saw is that when you start to combine different GSM signals, since they are all uncorrelated to each other, hopefully because they are different words being talked on each channel, what is going to happen, you know the law of the, I don't know the English word for that, but it's the law of great numbers from statistics, which means that if you combine different statistical variables, they will become Gaussian behaved. So what is happening is when they start to combine GSM signals, the peaks start to be higher. So what that means, it means that they should use the power amplifier much lower. If not, they will start to compress the power amplifier even if they are using the same average power. Okay, and this is quite important to consider in this case. So the other problem we have is the dynamic impact of multisigns. Why this is a problem? Because when we have a multisign, actually we are exciting different values. You see here, we are exciting different values of the video bandwidth. So actually, when we have this tone here is created by this mixing product, and if you look to this mixing product will generate a video bandwidth at delta omega, which delta omega is the separation between these two tones. If I look to this component, despite it will fall on the same position, it's another mixing product, is exciting a second value there. You see, the other component, the third value there, fourth value, and so on. So what I'm saying here is that when we use a multisign, I cannot say that this component comes only for this plus that minus that, for instance. It comes from a multitude of combinations that you can have here. And each combination will excite a different position on the graph. So the complexity starts to become very, very huge. Okay? And this is important. Why? Because if they all have the same point here, then with a single measurement I can capture everything. But now I have different values. So I should capture all the, you probably are familiar with Smith chart. I should cover all the Smith chart in that sense. So I will pass this, you'll have this later on, because I don't want to bother you with that information. But let me stop here on the graphs. And what is the main problem here? The main problem here is that, again, what I'm showing you here, and this is another problem, I'm showing you two multisigns with same power, with same statistics, and completely different spectral growth. Why? Because in one of the systems, I have what it's called a memoryless device. So my device that I'm using doesn't present any behavior at the low frequencies. And on the other signal I'm showing you, the memory device presents huge different values at low frequencies. You see? So what happens is that here I'm exciting, or in one case the point was here, or in this line, that is, it was a real point, not information about the phase, and all mixings were falling here. On the other side, the mixings were falling around the Smith chart, and you see that the distortion is completely different from one side on the other. This is another big problem. Which means what? It means that depending also on the tone spacing of the multisigns, I can have a problem. And you said, okay, so what I should do? I don't know. The best thing to do, from my point of view, is use the input signal as close as possible to the signal that you are going to use if you are going to use that device in a specific case in that sense. Okay, let me follow. And of course, these signs that I've been talking to you are all what it's called uniformly spaced. So they are all spaced with the same frequency separation, you see? So what that means? It means that if I want to capture a time domain of this waveform in an oscilloscope, I know exactly the period, I know exactly when they will repeat and so on, because they are uniformly spaced. What is the problem with that? The problem is this, is that when I want to do this, if they fall here, if I measure this tone has contributions from all these tones, so I cannot have information, I cannot separate information, you see? They are all falling on top of each other. So I can have strong algorithm schemes to do this, but it's not easy to separate these, let's say, these different components or these different mixing, because they are all on top of each other in this sense. So what can I do? I can use non-uniform multisigns. What is non-uniform multisigns? Well, for instance, here I have, I think in this case is a 10-tone multisign, where I have some tones there, some tones there. This is not a two-tone. It's a multisign where I have tones there and tones there, you see? But they are non-uniform. What is the problem with non-uniformity? The problem is that the period of the multisign in time domain will be the minimum multiple or minimum common multiple of the two tones, and it starts to be huge. So I will have, in order that this signal to repeat, so I can do the FFT and so on, in order that this repeats, I have to capture a lot of points. Okay, this is my main problem. So we come out with a possibility of, and this is going hugely to signal processing, but we can actually measure a non-uniform multisign with a technique that is called Gerber and Papulis technique. You probably don't know what it is, or probably you know, I don't know. But actually with this technique, what we can do in terms of instrumentation is that we can extract some frames, periodically extract some frames, and then with the least mean square extract the information of the amplitude and phase of each of tone. Why is this, I don't know if I have it here now, why is this important? Because, let me try to show you. With the three tone is quite easy. If you see, we have 1, 2, 3 tones. Omega 1, omega 2, omega 3, and I have distortion here. This is a combination of all these, right? So you'll have omega 3 minus, let me see, you have 2 omega 3 minus omega 2. You'll have omega 3 plus omega 2 minus omega 1. And you have omega 2 plus omega 3 minus omega 1 is the same. So you have these two combinations. In this case, you have these two. Okay, they will fall on top of each other. Why? Because this separation is the same, which means that omega 2 minus omega 1 is equal to omega 3 minus omega 2, which is equal to delta omega, which is the separation between them. So they will fall on top of each other. and I cannot separate them, okay? But imagine now that this delta omega 1 and this delta omega 2 are different, which means that these signals will be on top of each other, which means that one will be there and the other one will be near close of that. So I have the information separated on each other, so I can capture the dynamic effects easily instead of the other case, okay? This is why we are using this. But of course, when you do this, you need to capture a huge amount of time domain information, so you can do the FFT, and one possibility is to use the Gerber-Papoli scheme and extract this information, but of course, again, this will give another huge class here today. So, in conclusion, let's say that one-ton is mainly the extension from linear systems, so gives you very small information. Two-tone signals are a better choice, but for dynamic system, it does not allow to gather the information that I need. Multisigns are a very promising test signal, nevertheless extremely care should be put in selecting tone spacing and the phase of each tone. And signal statistics are a very promising metric for signal similarity and for test signal design, and of course it's an obligatory technique for this. So I'm open again for questions now.